So if I look at a problem like this, we have 6, 12, 24, and I want to figure out what the next couple are. So if I look at what's happening between these numbers, if I'm adding 6, well, this one now is adding 12, so it's not adding a common number. So what else could be happen? Well, I could multiply by 2 to get there, and if I multiply by 2, I'm getting to 24. So now, instead of a number being added, we're having the same number multiplied. That makes this a geometric sequence. So there's a common multiplier. So with that, my next couple numbers would then be 48 and then 96, because I'm multiplying by 2 each time. When we worked with these, then we also came up with equations for them, and it was a T of n equation because it was a sequence. And I need to figure out my zero term. My zero term, to do that, I need to go backwards to figure out what number would be here. And that number was 3. And then I have my multiplier of 2, and that's to the n. Now, we also started dealing with these where they were not sequences. And that means this is exponential. So if I look at just these numbers, and I think of it being like coordinate points of 1, 6, 2, 12, and 3, 24, the equation for that is going to be y equals 3, because that would be my zero term, times 2 to the x. But it's the same thing as a sequence. Now, another thing to think about is if my zero term is 3, how I get this term right here is 3 times 2, because 2 was my multiplier. This term is actually 3 times 2 times 2, otherwise known as 3 times 2 squared. This term now is 3 times 2 times 2 times 2, or 3 times 2 to the third. So what's happening here is my multiplier, I use my multiplier once, twice, 3 times, and so on and so forth. So I did 48, it would be 3 times 2 to the fourth. 96 is 3 times 2 to the fifth, and so on. So that multiplier, that's why that's the one that has the exponent. So when I look at y equals 3 times 2 to the x, well, whatever I put in for x, that's how many times I'm using that multiplier. So how that ties in with some of the things we did in chapter 7 was if I have a table. And let's say I have the numbers 5 and then 15 and then 45. I can figure out what my multiplier is, because 5 times my multiplier gives me 15. So this table is the same thing as if I would just write the numbers in order like this. So I have 5 times my b value equals 15. And I solve for that b value now by dividing by 5, and b equals 3. Which is why when we worked on these in class, we talked about taking a term and dividing it by the previous term. 45 divided by 15 equals 3. Term divided by the previous term gives you your multiplier. But as these got more difficult, that's why I showed what was here in red. Because understanding what's happening to the problem and with the problem can make the more difficult problems make more sense. For instance, what if we did not know that that was a 15 there? So I'm going from 5 to 45. That means that 5 times some b value gives me that number, and times some b value again gives me 45. So now I have 5b squared equals 45. And if I divide by 5, I have b squared equals 9, and the square root gives me b to equal 3 again. So I know my starting value. I now know my multiplier, and there's my equation. So if I had another table where it was 0, 3, 1, and then I have 2, and let's say I'm skipping both of these spots here, and this is now 24. So if I think of what's happening here, I need to use my multiplier to get to this number. I need to use that multiplier again to get to that number. And I need to use my multiplier a third time to get to that number. So this would be 3 times b times b times b equals 24. Also, we could write that as 3 times b to the third equals 24. And now I solve. I divide by 3. Those cancel out. I have b to the third equals 8. And now when I take the third root, I get my b value to equal 2. So now I have my 0 term. I have my multiplier to the x. So these are all tied together, whether it's written as a table, or if it's written in a sequence, or if I have a graph. And let's say the graph looks like this, and this right here is, let's say that number is 6, and let's say I have a value over here that is 2, and let's see here, 150. How about that? That means my y value of 6 got multiplied once to go here, and another time to get to this spot. So it's the same as 6 times b equals 150. Or 6 times b squared equals 150. And divide both sides by 6. B squared equals 25. And b equals 5. So the equation is my 0 term, my multiplier to the x. So all these really tie in together. Another thing I could do here is, what if I gave you just coordinate points? If I said I have the coordinate points 0, 6, and 2, 150. So they are the same coordinate points as this problem, so I can do it the same way there. I could also think of it as being in a table. So I could say that, oh, okay, I have an x and y values, 0 and 6, and then 1, but 2 is 150. So I'm using my multiplier twice. That's how I came up with that equation there. Yet another way that we figured out how to do this. So all these different ways work. I'm just giving you multiple options so you can see which one you like. These are all y equals a times b to the x. These coordinate points are x, y values. So if I put those in, my y value is 6 times a, b, my x value is 0. All I did was I took that 0, put it in there. I took my y value and I put it in there. So with this, b to the 0 equals 1, so a is 6. Once I know that a is 6, I now can go through and use my equation, but now I'll use it with this x and y value. So y is 150 equals a, but I don't want to write a because I know what a is. So instead of writing an a, I'm going to write 6 times b to my x value of 2. So now when I go through, if you notice, it's the same thing I have right here. So now I divide by 6, and I get 25 equals b squared, and again, b equals 5. So I can write my equation of y equals 6 times 5 to the x. So whether they're given to you as coordinate points, and we can set it up this way, or if it's given on a graph, or if it's given on a table, or if it's given as a sequence, they all follow the same pattern.